So the title of my presentation is Grain Flows over Wall-like Obstacles. And I would like to talk about induced patterns and the impact forces on walls. First of all, let's see a bit the background and the motivation of this research. So we need to design protection structures against large-scale flows, such as snow avalanches. We need to divert the flows, break the energy of the flow, and ultimately to stop them. So here in these pictures, you can see some large structures like stopping dam here in Iceland, in Neckar-Stadur, 2 rows of retarding mounds upstream the stopping dam. You can see here another stopping dam in Seyðisfjörður. Here 2 deflecting dams that forms a wedge to deflect the avalanche in 2 directions. I would like to attract your attention on the size of these structures. Here with my colleagues, we are on the top of the retarding mounds. Here you can see the bus that gives you the scale of this stopping dam. And here we are walking along the crest of these deflecting dams. So we are trying to fight against very large scale flows. Another interesting point is that in a site in France, in Tacona, in Chamonix Valley, close to Mont Blanc, we have equipped the retarding mounts with some force sensors and velocity sensors. So we are able to have the force exerted by these snow avalanches on the retarding mounts, and the red signal here will give you a typical signal we can get from these measurements. You can see that the pressure can reach value close to 1,000 kilopascal. That to say 100 tons per square meter, which is quite huge. My talk will go beyond the snow avalanches. We are very interested in snow avalanches in our unit, but we also develop some research for other types of large-scale movements, such as rock avalanches, as you can see in this figure in Canada, or ice avalanches, as you can see here in this figure, the 2 avalanches that occurred in 2016 in Tibet, and you can see that the deposit is rather granular. So anyway, generally, my research is dedicated to granular flows and implications for any kind of dry debris flow when the granular nature of the flowing material is primary. So before going into the detail of the understanding and the modeling of the interaction between free surface granular flows and wall-like rigid obstacles, I would like to discuss a bit depth average model. We are using a lot depth average models to try to predict such kinds of flow like rock avalanches, ice avalanches. And they are very common and very useful. That's what I want to explain here. And in particular, a big assumption is made, but this assumption is quite reasonable, is to assume that the variation across the thickness, capital H, compared to the variation along the main direction of the flow, capital L, so we know this epsilon, this ratio epsilon, is very small, which is quite very reasonable when we look at these types of flow here. And if we assume in addition that the flow are incompressible, we can depth average the local mass conservation equation and the local momentum conservation equation. And we can arrive at a rather simple system, which is here a system of equation with the mass conservation and the momentum conservation. So this system helps you to describe in a reasonable way the variation of the flow thickness as a function of position and time, and the variation of the depth average velocity, u bar, as a function of position and time. And in the end, the inertial forces are balanced by 3 main forces: the gravity force that push the flow down, the force associated with the flow depth gradient, and a resistive force, which encapsulates the rheology of the material at stake. So for example, for dry grain flows, you can derive some friction law, as the basal effective friction will be a function of in turn of the velocity, the thickness, and some typical angles. So I won't go into the detail of this friction law, but you, in principle, you can describe with this type of model many types of geomaterial if you are able to infer the right friction law. So here I show an example of this simulation. So we are simulating an avalanche, a snow avalanche based on the rheology of Volney, which consider two terms, a friction coefficient plus a turbulent term with a turbulent friction Xc. So we are able with this type of model to describe, for example, the spreading of a big snow mass into a snow avalanche system, which is recalled here in the picture. So this is the picture I already showed in Tacona in Chamonix Valley with big retarding mounts, some storing platforms and a lateral dams and a stopping dam at the end. So we can reproduce quite reasonably well this kind of interaction with some shocks forming against the wall. So we come back to these shocks and jumps formed when the flow impacts the wall. So I show here two other examples with this kind of model. We are able to reconstruct past event. So here, this is the ice avalanche in Tibet, one of the two avalanches in Tibet, and we are able to reconstruct the spreading of the mass, the final run out, thanks to this type of model. We are also able to predict some scenario when you don't have a big amount of data. For example, in a very remote area, here in a high mountain hut in the Pyrenees in France, we need to construct scenarios to design a protection against avalanches. And these models are very useful for that. But of course, these models, that's why I introduced with this kind of model, have some big limitations. When you put an obstacle into the flow, you disturb a lot the flow. And of course, the initial assumption, which is that epsilon is much smaller than 1, becomes false. So epsilon becomes of the order of 1 in this type of interaction. Also, when the flow impacts the wall, you have some complicated processes, like the formation of dead zone upstream of a wall, or the flow detachment, so the formation of jet upstream of the wall. And the density in the dead zone area can be much higher than in the typical incoming flow condition. And also in the jet, it can be much lower than the typical incoming density. So for all these reasons, the initial assumptions of the depth average model are not respected. So that's why we need to develop alternative approaches. So of course, there exist some other more complicated 2D models, but this is not the topic of my talk today. I would like to try to still stick to the depth average approach and try to describe the key processes that are at stake when the flow interacts with an obstacle based on a depth average approach. So I will consider 3 key patterns: the standing granular jump, the propagating granular jump, and the airborne granular jet. So first, let's start with a simulation of a standing jump. So it's a DEM simulation based on discrete elements method simulation with the YED software code, which is developed by our colleagues in 3SR in Grenoble. So we are running some simulation where grains are going along a slope, and we have a wall at the end, which we artificially open at the base to make a stationary jump. So the jump is not moving over time and over space. So with this, we can repeat the experiments, the numerical experiments or the lab experiment many times and try to look at the property of these jumps. So what is a jump? In fact, this is a transition from a supercritical flow to a subcritical flow. So the supercritical flow is defined by a full number which is higher than 1. And the subcritical flow is defined by a full number which is smaller than 1. It means that in this subcritical flow, disturbance can propagate downstream, but also upstream. In principle, in general, those jumps, they are described by a mathematical abstraction. This is what it is implemented in data average model. In fact, we assume that the length of the jump is 0. There is a shock. So the volume of the jump shrinks into a singular surface, as it is shown in this sketch. In addition, we generally assume that for shallow water equation, for example, we assume that the density is constant across the jump. So the typical shock equation for shallow water flows is here. And in the particular case where the jump is steady, when the propagating speed is 0, you get the very classical Bélanger equations that gives you the jump height ratio, h star over h, as a function of the full number. Note that this kind of framework can be extended to deflecting walls when you have oblique jump formation, but I won't go into the detail of this particular oblique jump here. I'm more focused on the normal jump when a flow impacts a wall that spans the width of the chute. But in fact, when we are studying these jumps, either with numerical experiments, with DM, or with laboratory experiments, as we did in the frame of the PhD thesis of Ségolène Méjean, for example, and using the X-ray radiography, which is developed at the University of Sydney, we are able to measure the density across the jump, the evolution of the density across the jump. And the depth average density can change a lot across the jump, as you can see in this blue curve, where you start with a flow which is about 0.4 in volume fraction, and that's reached 0.5 or 6 in volume fraction in the outgoing flow. So clearly there are some sharp density gradients across the jump. So there is density variation. And the length of the jump is far from 0. At high fluid number, we have values at about 30 diameters. And when you decrease the fluid number, the length of the jump is increasing. So clearly, we need to take into account the density variation across the jump and the length of the jump and the force acting inside the jump. And also maybe we have some anisotropy of the normal stresses across the jump because the material change, the distribution of the stress distribution is changing across the jump. So to describe this, we propose to consider mass conservation and momentum conservation, but we include density variation. So you have rho star and rho, which are different before and after the jump. And you have the force acting over the jump, mainly the force due to the weight of the jump and along the slope, and the resistive force, which is encapsulated into a Coulomb stress. So you introduce an effective friction inside the jump. With this, we arrive at a third order equation that can be solved thanks to Cardano method. And we have a more complicated equation like this. So h star over h is a function not only of the full number, but also of all the parameters introduced in the framework. So in particularly the density variation, the difference between the tangents of the slope and the effective friction, and the length of the jump relative to the flow thickness. So this equation can be used to try to estimate the effect of different parameters. In particularly, we can look at the effect of density variation. And typically for a given full number, if you plot the jump height ratio as a function of the full number, for a given full number, an increase of the density ratio will lead to a decrease of the jump height. So compressible jumps are smaller than incompressible jumps, which makes sense. You can also look at the influence of the length of the jump. So at a given full number, jumps that are more diffuse, longer, have a higher height. And you can also look at the effect of the variation of the stress anisotropy, the anisotropy in normal stresses, also as it is depicted in this plot. So, okay, now I will move to a situation which is more common when it was a kind of idealized situation, the standing jump. Now I move to a situation which is more common, which is the propagating jump. So here you have a flow going down a slope and meeting a wall, and you close the chute at the end. So a jump is formed and propagate upstream. So I will use the images extracted from this short video, which is a lab experiment, to explain what happens. So at the first time, the flow is arriving, then it impacts the wall. Very shortly, a big jet is formed, a vertical jet. And after a very short time, we see the occurrence of a jump. So a jump is clearly formed and start to propagate. And there exists a long phase duration during which the jump is propagating at a rather constant speed, Vn, as shown in these different pictures. And in the end, when you don't have any more supply of mass in the incoming flow condition, you reach complete cessation of the flow. So as for the standing jump, those jumps, they have a finite length, L. And there is density variation, a big density variation across the jump, because you start with a flow which is nearly dense but a bit dilute, and you go to static condition with a dead zone form. U bar star is 0, and the density is very high. So the flow is compressed here. And you can also develop the equation of conservation of mass and momentum and introduce the forces that are acting through the length of the jump, so the weight of the jump and the resistive force of the jump. You can also introduce the variation of density through rho star and rho. And with this, you can arrive again at a third order equation. I don't show the detail. And you can solve this equation again with Cardano method. And you can have the jump height as a function of the full number, the density change, the difference between the tangents of the slope and the effective friction, etc. And here I plot the jump height as a function of the full number in case of steady condition in dashed line, and in the case where the jump propagates upstream. And clearly, this propagating jump is a bit higher in general for a given full number than the corresponding standing jump. Okay. So here in this situation, I recall this typical situation where you have a big flow which is very fast that impact a wall which is very high. So the height can be considered as infinite because the flow cannot overflow. The full number here is 12, so it's a very supercritical flow. So you form a jump that propagates upstream. And if you decrease the height of the dam, at some point, you can allow some overflow. The flow is able, the grains are able to overflow the dam, and a bore is propagating upstream, and at some point will stop. So you can have a steady jump form and coexisting with a jet downstream. And if you increase, you still continue to decrease the wall height. At some point, the jump is no longer propagating. You have all the material is launched up downstream of the wall, and you form a big airborne jet. So there exists a critical height of the wall below which this airborne jet will be formed, and above which the granular jump still propagate upstream and form a standing jump. We can show that this critical height of the obstacle can be approximated by the jump height minus the full number divided by the critical full number at the power 2/3. So these equations are developed in the PhD thesis of Christine Martin-Conavotir, and I extended this to situation where I want to account for the weight, for the force acting across the jump, so the weight of the jump and the frictional force, resistive force inside the jump. With these two equations, these two important equations, so the jump height, either the jump height, equation 1, and the critical wall height below which a big airborne jet will be formed, we can construct a phase diagram for the flow wall interaction, for the granular flow wall interaction. So equation 1 is there. I plot the equation 1 for a given set of parameters for tangent of the slope, the effective friction, and so on, the length of the jump, the density variation. So there is some possible variation of this line depending on the choice of the parameters. I plot the other equation here, which is lower than the first one, which give a prediction lower than the first one. And then I can define the frontiers between different zones where I have different flow wall interaction regime. And below equation 2, you will have big airborne jets without any jump propagating upstream at very high Froude number. And if you increase the wall height, the energy of the jet will decrease. There will be smaller and smaller, and the jump will be able to propagate upstream and reach a steady condition, forming a standing jump in the gray area here. And if you increase again the wall height, overflow will be prevented. You don't have overflow downstream, and the jump will propagate upstream, and you will form a bore in an unsteady regime. And if you decrease the Froude number, at some point, the flow is no longer supercritical, and you can form dead zone coexisting with jet. This is a very particular situation. And to be honest, we really need to understand much well this. And the frontier between the dead zone, the standing jump area, the bore area, and the airborne jet area is not so clear. Okay, but anyway, this phase diagram is very useful to have an idea of what flow wall interaction regime will be at stake. So now I move to the second part of my talk. From this, can we have some information on the impact force on walls? I would say yes, and I will show you why I'm positive on this. So the question is, we know the flow, for example, from the depth average flow model, we know the reference flow. So what is its typical flow thickness? What is its typical depth average velocity? Maybe if we use a compressible model, we can have some information on the density of the incoming flow. And with this, we would like to estimate what will be the impact force of the flow on the wall. This is a very challenging question, and I know that many people in the group of Hong Kong are working on these questions as other groups. But here I want to tell you that based on the phase diagram of the flow wall interaction regime, I think that the question can be solved with some good accuracy. So I want to explain this. If you know where you are in this phase diagram, I think that you can be able to know what will be the framework to be developed to derive the force. So that's what I want to show through two examples. The first example is the gentle overflow of grains passing over a wall with the formation of a well-defined dead zone upstream. So let me explain this. Here I go again to the phase diagram. So the relative wall height as a function of the Froude number. And I'm in this area where typically I will form dead zone. I know that the Froude number is not so big, so it's about 1, but it can be a few units. And the obstacle height is not so big too. It's about 1 or a few units. So I will get a dead zone regime. So the typical sketch of this flow wall interaction regime will be this one and not another one. A dead zone forming upstream of the wall and a jet downstream. And with this sketch in mind, I can define a control volume, which is in gray colored here, and I can apply mass and momentum conservation to this control volume. And we can show that the force in the end is the sum of 4 contributions: a dynamic force, which is proportional to the square of the incoming velocity, a hydrostatic force, which is proportional to the height of the incoming flow, the apparent weight of the volume, the control volume, so which involves some friction, and eventually the force due to variation in momentum over time if the incoming flow conditions are transient. So this type of model was validated on DM simulation for steady flow conditions. It was validated on DM simulation for unsteady flow conditions. And we also validated it on lab test. So I refer to the publication on this topic. And with this type of model, then we can go to the equivalent drag coefficient, which is defined as the force on the wall divided by the typical kinetic energy of the flow. So this equivalent drag coefficient is the sum of a purely fluid coefficient, a constant seawall, plus a kind of earth pressure coefficient divided by the square root of the full number. And here you have the analytical expression of each parameter, so each coefficient, seawall and K-wall, and you can plot this equivalent drag coefficient as a function of the relative height of the obstacle for different full number conditions. So you have a full description of these coefficients that are function of the incoming flow condition and the geometry of the obstacle. Such an approach can be also developed for other types of interaction. And here I show a second example. So this is the impact of a grain flow against a wall with a granular bore, so a propagating jump that developed upstream of the wall with no overflow downstream. So here again, I go to the phase diagram. So the full number is very high. I have supercritical condition. And the height of the wall is infinite. So I have a big, very high wall that prevents overflow downstream. So I'm somewhere here in the green area. So here the pattern is this one and not another one. You will form a granular bore propagating upstream with a velocity Vn. And if you, again, use mass and momentum conservation equation in a control volume that encapsulate this granular bore, you can arrive at the prediction of the force on the wall. And the force on the wall is mainly the sum of 2 components. So a force due to the shock, which is a dynamic force proportional to the square of the velocity. And you have the force that develops, another force which is developing, which is the apparent weight of the mass which is stored between the wall and the jump, the shock, which is FdZ, which is again a function of some friction. So here, this model was validated on DM simulation. So you can see here some DM simulation of a flow impacting a wall. Then the jump is formed. The gray or white zone are grains in static condition. The orange are grains moving and that are moving and that are incoming before impacting the wall. And the green area is the length of the jump between the static zone and the incoming inertial flow. And with this model, again, you can go to this definition of an equivalent drag coefficient. So the ratio of the force relative to the kinetic force, which is again a sum of 2 terms, a purely drag coefficient, seawall, and an earth pressure coefficient divided by the square of the full number. So, and you have analytical expression for these two coefficients, the first one being a function of the jump height, and the second one being a function of the length of the bore, the density variation, and and the jump height through the height of the static zone. So it's important to note that these coefficients are dependent, okay? So now I can conclude on my talk. So a phase diagram for granular flow wall interaction was proposed. The key input parameters are, first, for the case of a wall, the relative wall height, so capital H over H, the Froude number, and there are other more or less secondary parameters that are needed. An important one are the density variation across the pattern which is formed. This is the friction. You always need some friction somewhere. And the anisotropy in normal stresses. I think that this phase diagram is very helpful to identify the key patterns at stake and thus to characterize the flow wall interaction regime which is at stake. And I think I try to demonstrate that this is a crucial step to move forward and calculate the induced impact force on the wall. If you know where you are in the phase diagram, you know the key pattern which is prevailing during the flow wall interaction, and you can infer a relevant expression for the force into the wall. So I demonstrated this through two examples, the gentle overflow with a dead zone and the granular bore. So I think that when the key pattern is well identified, this is a take-home message, the relevant prediction of the impact force can be performed. So this framework, I think, in the future can be extended to more complicated geometry. We are working on this. I think it's really important to try to push forward, when it's possible, the development of analytical solutions for this kind of problem, even if they are complicated. The analytical solutions are very useful to give reasonable results and to understand a bit the main physics. Of course, this has to be done in parallel with advanced laboratory experiments, and dynamics X-ray radiography, as we are using with our colleagues in the University of Sydney, is very useful. And of course, full 3D computation. I think this aspect will be the topic of the symposium. So like SPH code, MPM, or some couple method between DM and SPH, DM and SPH are needed to be developed and conducted in parallel. So I thank you very much for your attention, and I'm again sorry not to be in person in Hong Kong today, but I was very happy to participate even if it's remotely, and I invite you to contact me through email if you want to have more details or questions about my presentation. I thank you very much for your attention.
Thank you, Dr. Thierry Faug, for the second keynote lectures on the interaction between a grain flow and obstacle. I think he has rightly pointed out that apart from learning from monitoring data, as Professor Faug has lectured before, domain knowledge, some people call it domain knowledge, that is the physics behind the observation monitoring data is also very important, and it is widely the right topic to our symposium on the predictions, make us to have a better prediction in future.